Be a short explanation of Wein's law and the Stefan Boltzmann's law and the applications we need to know. So you remember we went through these slides in class, and now I just wanted to make sure I brought home all the points so you could review and make sure you understood. So both of those laws are in reference to radiation, or the type of heat transfer that involves creating electromagnetic waves. And so that's quite a complex thing. But first, we'll do a quick review of conduction and convection. Conduction is the type of heat transfer that goes from a hot body to a cold body, and there has to be some contact in order for conduction to work. If you jump in a swimming pool on a hot day and it feels really cold, it feels cold because of conduction. Your body is warm and it's used to the warm outside air, then it goes into the pool that's not so warm and you start losing heat. So you would be the warm body heating up the colder body of the pool water. And so that can happen in solids, liquids, or gases. Anytime two molecules touch, the one with more energy gives some energy to the one with less energy. And the second one is convection, and this does not happen in solids. This only happens in liquids and gases, and it's when you start getting circular patterns of rising and falling materials due to differences in density. So when things are warm, they are less dense, and so they're going to rise. Inside the Earth, this happens, and your mantle heats up, it goes up, and then it cools down, and it makes a circle pattern, and that's where plate tectonics comes from. This happens when you boil water. This happens if you ever watch clouds form and you see a thunderhead forming. You can see that it's due to differences in density, that warm air is rising, and then it cools down and you get condensation, and some pretty cool cloud formations form as a result. So that's spreading out heat. Both of those things are spreading out heat, trying to go into thermal equilibrium. The last way that this happens is radiation. And I want to talk a bit about what a black body radiator is. These are solid objects, or objects that light shines on. It doesn't matter what type of light. But a black body radiator is something that perfectly absorbs all incident light and then re-emits that light based on the temperature that it is at. If that black body is in thermal equilibrium with its surroundings, it will always produce a consistent output. You can identify what color it is, and it will always appear that color because it is in thermal equilibrium. It is absorbing and re-emitting light at the same pace. They might not be the same wavelengths, but they are, because they're in thermal equilibrium. My radiator is not heating up or cooling down. It is just going to produce its own light based on that. And the way this is often modeled is if you have a box with a small hole, and then light that goes in that box is not going to escape. It is going to be absorbed somewhere. It's going to bounce around. That light comes in, but reflects off the back, and it doesn't ever leave. And that's a pretty cool thing. But then you give it enough time, you shine enough light on it, and that temperature is going to increase until it matches whatever energy flow is happening into that box. And that's okay. So, and that's what's going to happen. But then if you would watch that hole, you would eventually see light start to come back out. It probably would not be visible light, but that light would be in reference to the temperature inside of that box. So it has absorbed some energy from that incident radiation, and now it is going to emit radiation. And the amount of radiation that it emits, or the frequency of radiation that it emits, is entirely based on the temperature inside that box. You heat that box up enough, and it will start to glow on the inside, and this is how potters have worked for years and thousands of years. When they're using kilns, they base their temperature inside on the color that they see. They heat it up enough that it glows a certain color, and that's where our opening slide was from. they would know when to pull out their pieces based on the color that they see, because that color represents a certain energy, a certain amount of temperature. So a black body absorbs light and re-emits light, all based on the temperature of the box or the object. That's what color it's going to re-emit. And it's going to appear black to us. That's why it's called black, because most things are not going to be hot enough to produce light in the visible light spectrum, because that gets really warm. So when we see a piece of charcoal or most black things, they can be understood as black bodies because they are absorbing lots of that incident light. Nothing is a perfect absorber, but they absorb a lot of it. And then they feel warm because they are going to re-emit that energy based on how much energy they've absorbed. If you have a white thing, something that's white, it feels a lot cooler because it is reflecting that light. It is not absorbing that incident light, and therefore its temperature will be lower, and the wavelength that would give off would be lower as well. Or sorry, wavelength would be higher, the frequency would be lower. All right, so when things start to heat up, you have to remember what's going on. All things are made up of atoms, and as their temperature increases, those atoms are going to start to vibrate more and more and more. And as you have moving parts, then it's not so much atoms that we're worried about, it's these electrons that are on the outside of the atom. They're going to be moving with the atoms, and anytime you move a particle with charge, you get a change in electric field. And that change in electric field is going to be the outgoing photon that we see. So this is not atomic spectra where electrons are jumping energy levels and you're producing a specific color. This is just based on the random vibrations inside that object due to its temperature. So because those things are moving, they have charges. They are causing a change in the electric field, and consequently, due to Maxwell's equations, a magnetic field. And then when you look at that, you see that change in fields. And this is your eyeball, in case you didn't know what that was. And you see that is light. If the frequency is right, you say, hey, that's a certain color. If the frequency is lower than what you can see, it doesn't look like any color at all because it's in the infrared or microwave spectrum. So based on its temperature, that determines how much vibration can happen, and those vibrations cause electromagnetic waves that we see. Because temperature is a type of energy, and when you start increasing the frequency of light, you increase the energy of the light that it is being produced. And so that's where we get our whole electromagnetic spectrum from. Low energy waves, long wavelengths, low frequency radio waves, all the way up to short wavelength. High frequency gamma rays, we see the visible light spectrum. And if you have black body radiators doing all of this, low, very, very, very low temperature radio waves, very, 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 very high temperature gamma rays. You'll never get gamma rays produced by black body radiation. Temperatures just are not that high. You can get visible light, you can get ultraviolet light, but not much more than that. And that is due to some fun little things and introduction into the world of quantum. But that's not the purpose of this. I'll mention it again in a few slides. But the purpose of this is to talk about why we see this radiation happens and what we can do with it. So there's just a little more breakdown of the colors that we see. And red, low energy light, is cooler than high energy light. So cooler temperature, higher temperature. If you have a black body, you look up in the night sky and you see a blue star. It's a lot hotter than a red star. Most stars are yellow or orange, or they appear white because they're producing in the middle of the spectrum, which you'll see in a second. That means they're not only producing a single wavelength of light, but they're producing a range of colors. And that range of colors makes that star look white to us because our eyes work that way. So now we're getting into our first law. And this is looking at the relationship between the wavelength of light that is produced and the temperature. And it was experimentally validated that if you heat something up to a certain temperature, you can predict and produce, mathematically calculate the wavelength of light that was made by that object. And this is using a constant called Wien's displacement constant. But it's a fairly simple relationship. If you increase the temperature, that means your wavelength gets smaller, because we can say that temperature is inversely proportional to wavelength, or wavelength is inversely proportional to temperature. If we're talking about frequency is proportional to temperature, because if your frequency increases, your wavelength decreases, because we're talking about light and the speed of light doesn't change. But increase that temperature, decrease that wavelength, increase that temperature, increase the frequency, and the rate of change of that is going to be based on Wien's displacement constant. And that has been experimentally validated, and you can use this relationship to solve for temperature or wavelength. And we could test this Wien's displacement constant in the lab if we wanted to. If you're able to identify wavelengths and look at different temperatures fairly accurately, you could try to validate that Wien's displacement constant, which would be pretty cool. But I'm going to go to a simulation for this. And this is just something from PhET that I can change the temperature. So over there is temperature, and you're seeing, let me get my graph values. This is the temperature here. And as I increase that temperature, you can see that the maximum wavelength, the peak of that graph, is getting smaller. The more I increase the temperature, the smaller and smaller value that gets. I'd have to zoom way out in order for you to find that. Now it is in the UV part of the spectrum. If I cool that object down, get down to the sun, where's that? That's right in the middle, about green light. So because it's producing not just green light, it's producing this entire range. That is why the sun, our star, looks white to us during the day. If I cool things down even further, I get down to an incandescent light bulb. Oh, that's really cold compared to the sun. And that's why incandescent light bulbs give warm colors. They're not bright whites like fluorescent light bulbs, but because they're using temperature as their source of light. And so they're going to make all colors of light, yes, but it is primarily reds and yellows, oranges. And so that's going to give us a nice warm light. But LEDs or fluorescent bulbs, sometimes those give us really cool lights because they are using emission spectra rather than heat as their wave source. And we'll get more into what I mean by that later on. But yeah, I just wanted to show you this so you can see that as temperature decreases, the maximum wavelength, the peak wavelength, increases. So it's going to the right, so that means the wavelength is increasing. But that means our frequency decreases, the energy is decreasing. All right, so, yeah, and we can zoom in and see these at different points. Get all the way down to Earth, and the Earth is really cool. 300K, it's barely making a bump. I'd have to zoom way out and way in order to find that. So the color of light produced, we can't see that color of light. It's not even visible. That part is gone. Not very much. The intensity of light is really small. Yeah, but you can see it's not a complicated thing, not a complicated relationship. So let's go back to this. And what you need to know is if you increase the temperature, you're shifting this intensity graph to the left, and you're also getting more power out because it has more energy to release, so your intensity increases and it shifts to a smaller wavelength or a higher frequency. There's a big problem with this because of classical mechanics is the only thing that actually exists. This, what we see based off experimental data, does not match what was observed using classical understanding of energy. And that was the Rayleigh-Jeans law, and it led to something called the ultraviolet catastrophe. I will give you some links so you can learn more about that, but this was the introduction to quantum mechanics and Planck's constant, saying that, we can't have any energy that we want. Energy is quantized, and there is a smallest possible energy, motion, smallest possible motion that an atom can have. And that smallest possible motion or action is called Planck's constant, but that is a quantized effect that we'll learn more about later on. I just wanted to throw that in to show that there are some interesting things from this. So I mentioned this word intensity, and that is not a hard concept either. The amount of power given off per unit area is the intensity of your object. So power is based on the temperature. Area is based on your object. So if your object, you're talking about the sun, your area is really big, but your power is also really high because it's really hot. And that we can figure out what the intensity from the sun would be. Yes, so when I use that word intensity, that's just what I mean, the power per unit area. And the last thing, the Stefan Boltzmann law. This is another relationship, and it's looking at the power given off and how it relates to the temperature. There's another constant here, the Stefan Boltzmann constant, that little sigma value. This guy right here. And that relates how much power, it helps figure out if my temperature is to the fourth power. So my temperature increases by 1 degree, my power changes by quite a bit because of that fourth power relationship. So we're just looking at how much power is given off and its ability to change by temperature. Then you have this constant that makes it, because we're talking about light, it gets it to really small values because light is not, a single photon does not have a lot of energy, and that's where that's coming into play. There is this other idea here of emissivity, and I'll talk more about that on your next slide, because nothing is a perfect black body. If it was a perfect black body, your emissivity would be 1, and it's going to emit 100% of the light based on its temperature, but things are not. They don't have emissivities of 1. They have emissivities of less than 1. Most things don't have emissivities of 0 either, where they give off 0 light based on their temperature. So those values will be between 0 and 1. Most things are going to be 0.5 to 0.8, 50% to 80% of the light, or of the temperature, is going to be given off as light. And then you have this A, and that is area. Oftentimes you'll see this rearranged: power over area equals emissivity, Stefan Boltzmann, temperature to the fourth. Why will you see that? Because that right there equals your intensity. And so, that's just an interesting little conversion that will happen a lot. But sometimes you want to know per unit area. Sometimes you'll want to know the total power released based on the size of your object. The questions you might see can move those variables around a little bit, and that's an easy one to move. And when we start talking about the solar constant, that is always intensity, and so yes, if you know intensity, you can just replace that, and intensity will equal emissivity, Boltzmann constant, temperature to the fourth. So yes, a lot of things with that. And I think that is, I had to talk about emissivity. So emissivity is the amount of radiation that is given off. Nothing is a true black body that gives off 100%. Nothing is a true white body, which gives off 0%. Almost everything is a gray body, so somewhere in between. All right, I hit you with a lot of information. So to recap, I don't think I put a recap page. This is kind of a recap page. So recap, let me write recap in. Recap. Radiation is transfer of heat energy, or energy, we'll say transfer of energy by turning thermal energy into light. And when that happens, the color of light that you see, or the wavelength of light that is produced, is entirely based on the temperature. You increase that temperature, yes, you're getting more intense light out, but you are also moving your wavelength, your peak wavelength. There's a peak wavelength, there's a peak wavelength, there's a peak wavelength. That temperature is increasing, and it is being shifted to the left. My wavelength gets smaller because it takes more energy to produce those higher frequency lights. And if, yeah, so more energy, because there's more energy when it's 350 degrees, 350 Kelvin versus 300 Kelvin, the peak intensity or peak wavelength is going to be shorter because it has more energy. All of your atoms in the system have more energy. The second thing is the intensity of light. The intensity of light given off is equal to emissivity, Boltzmann constant, temperature to the fourth. So if your temperature goes up, so the temperature is increasing, your intensity, you can see that intensity value going up quite a bit. And it's not a linear relationship at all. It's to the fourth power. So yes, so if your temperature goes up, the intensity of the light goes up to the fourth power at that rate. So the intensity is proportional to the temperature to the fourth. Then you have this other competing factor, the emissivity, which is based on the property or the properties, the materials that object is made up of. So if you have an emissivity, first, all of these peaks are at the same wavelength, but if you change your emissivity, so that is an emissivity of 1, a black body at this temperature at 300 K, then you have emissivity of 0.8, so 80% of that, emissivity of 0.2, so 20% of that overall intensity would be given off. So that just means less light is emitted, more light is retained, and that object will cool down slower based on radiation. So yes, that's a good summary of everything that you need to know from this part of 8.2. Thank you for watching. Let me know if we have questions. We'll be doing some practice problems in class.